Okay, so this lecture we will be talking about a paired samples, or also called related samples t-test. So for this, what we will do is we will define what paired samples t-test is and under what conditions will we use it, and how to go through the process of actually computing and applying the paired sample t-test. So let's conceptualize this, and first let's relate this to the single sample t-test. So this is similar to the single sample t-test and similar to all t-tests, where we're comparing two means to one another. In the single sample t-test, we're comparing a sample mean to a population mean, or we're comparing a sample mean to a hypothesized number, right? The difference here in a related samples t-test is that we're not comparing to a sample. We're not comparing the sample to a population. What we're doing here is we have two different uses for the related samples t-test. Number one, it compares two means of the same sample, measured twice under different conditions. So oftentimes this is something like a pre and post test. So for example, something like taking your as a student's GPA before coming into my class and after leaving my class, and asking the question, are these GPAs significantly different between these two time periods? Another way to do this is comparing two means from a matched or paired sample. And so what we do here, and so this is also why this is called a paired samples t-test, is because we're pairing people who are identical on similar or similar on some particular characteristic. And you'll see what I mean. So let's conceptualize number one, right? So let's conceptualize the first component of this, comparing pre and post tests. So here's an example. The weight loss program HYPOTHESES was interested in knowing if their program was effective. To test this, they weighed the 10 participants of their 2014 program prior to beginning the program, so a pre-test or a pre-program, and then weighed them again after program completion, also called a post-test, and compared the participants' average weight both pre and post-program. So what we're doing here is we're comparing two different means, but of the same sample. And again, what we're still doing is comparing the difference between the two scores, right? So this is very similar to what we did with the single sample t-test. So what we're doing is we're taking a sample of people out of the entire population and basically testing them at time 1 and at time 2, and then comparing sample means both pre and post program. And here's the other use of a paired samples t-test. Professor Collins wants to know whether online lectures are more effective than in-class lectures. He pairs students in the class with the same GPA. So what we do is we pair two students with a 3.5, for example, and splits them by placing one of those people into an online lecture course and the other one in an in-class lecture course. He gives all students in both classes the same midterm and compares the mean scores in the online lecture course to the mean scores to the in-class lecture course. So again, we're comparing the mean of paired students, and in this case they're paired on GPA, having the same GPA. So what we're doing is comparing online students with an online lecture versus students who have in-class lecture. So we're taking students out of a population and splitting them where they have some sort of similarity between the two, and in this case it's paired by GPA, and then we're comparing the sample mean of the paired samples, right? So this again, paired samples t-test, we're comparing the mean across those paired samples. So just to recap on the definition here, a paired samples t-test either compares two means from the same sample, usually pre and post, or compares means of paired samples, so people who are similar on some characteristic. Now let's get into calculating the paired samples t-test. So as you remember, and sort of taking us back, the paired samples t-test, like all t-tests, the 3 t-tests we will be discussing in this class, is this basic equation here, where we're taking the mean of group 1, subtracting the mean of group 2, and dividing that by the standard error of the mean. So the way you get this in the different types of t-tests vary, right? And so we'll go over the paired samples t-test version here. So let's use an example. So Professor Collins wants to know whether students' GPAs change significantly as a result of taking his class. To test this, Dr. Collins will compare his students' GPAs prior to taking his class, so we'll take the pre-scores with a mean and standard deviation, to their GPAs afterwards, post-scores, with a particular mean and standard deviation. And so we have our sample, right, students in my class. We have pre-GPA versus post-GPA, and it's non-directional. So we're asking the question, does it change significantly? We're not indicating whether better or worse. And so here we're going to use a two-tailed test instead of a one-tailed, which would indicate direction, right, directionality. And so let's state the null and research hypotheses here. So symbolically, what we're saying is that the mean will not change, or what the mean, so our research hypothesis is that the mean will not be equal to 0, meaning the difference between the two means are not equal to 0. The null hypothesis, symbolically, is saying that the mean difference will equal 0, meaning there is no difference between the two samples, the two paired samples. Verbally, for our research hypothesis, we would say something like, Dr. Collins' students' GPAs change significantly after taking his class. Whereas our null hypothesis would be something like, Dr. Collins' students' GPAs do not change significantly after taking his class. So just to reiterate, Dr. Collins' students' GPAs do not change significantly after taking his class. And so this is effectively the same hypothesis as the single sample t-test, right? No difference between the two means. First, we have to define the critical region. And this is defined by the degrees of freedom. And so, as you can see here, the related sample degrees of freedom is the same as the single sample degrees of freedom. It's df equals sample size minus 1. And so what we do is we use appendix B to identify one or two-tailed critical values. So in our case, the degrees of freedom is the number of paired scores, right? So our degrees of freedom equals 9 in this case because we have 10 scores, 10 paired scores minus 1. And we use our two-tailed significance test. So what we're doing is we're looking for a critical region between, or a critical region of 2.2622. So if our t-value falls beyond this, we can say with 95% confidence that there is a significant difference between the two scores, between the pre and the post scores, the post GPA scores. So let's look at our GPAs. So let's say these are all of the GPAs in both classes, right? This is the pre-class GPA. This is the post-class GPA. And so what we're doing here is we're taking pre minus post, or excuse me, post minus pre in this situation. And we do that because we're interested in looking at change over time, right? So in this case, we take the post score minus the pre-score to give us our D-score, or our difference score, our deviation score. And then after we do that for each score, we sum all of that up, right? So this is one of the reasons, just a sort of side note, why we want to do something like use a statistical analysis tool like SPSS. Because if we have, say, 100 different pairs, it's going to take us forever to have to calculate each of these. So using something like SPSS does this very quickly and easily for us. So after we calculate our D-score, we then sum our deviation scores. So this is the sigma D here. So it's the sum of the deviation scores. Then what we need to do is square those deviation scores. So pre and post, the difference between the pre and post. We square those, and then we sum those together, and we get the sum of the squared deviation scores. So this little symbol here will represent that, the sum, sigma, of the squared deviation scores, right? Sigma d squared is the sum of the squared deviation scores. So after we get that, we then need to compute our test statistic. And our test statistic takes several steps. First, we find our the average of the deviation scores. And the way you find that is you take the sum of the deviation scores and divide that by our sample size. So in this case, our average deviation, or average difference between the means, is negative 0.09. 3C, we compute the average sampling error. So this is our SEM, right, our standard error of the mean. And so we do this by calculating the sums of squares of the deviation score, and we do that with this calculation here, this formula here. So this is the sum of the squared deviation scores minus the sum of the deviation scores squared divided by n, right? And so this is very important because this part is the sum of the squared deviation scores. So the second part of the calculation earlier, and this is the sum of the deviation scores, the first part of the calculation, squared. So when we add that all up, when we do that calculation, we get 1.24, or excuse me, 0.124. Then we take the standard deviation of the deviation scores, sort of redundant, and we do so with this calculation here. Take the sum squared of the deviation scores, which we get here, throw that in there, and when we add our calculations up, we get 0.117. Then using these two calculations, we can get our, okay, excuse the typos there. So using this calculation, we can find our standard deviation of the deviation score, which is 0.117. And using both of these above, we find our standard error of the mean using this formula here, which is 0.037. So then our final step is actually computing the test statistic for our paired samples t-test. And so what we do is we take our mean deviation score, divide that by the standard error of the mean. So this mean deviation score, right, is essentially the difference between our mean 1 and our mean 2, our mean of group 1 and our mean of group 2. So remember back that calculation, the sort of standard formula that I told you about. And what we come up with in our calculation is negative 2.43. So again, our mean deviation score is step 3b, standard error of the mean is step 3c. And so what we do is we compare this to the critical region. We ask ourselves, is this negative 2.43 less than negative 2.2622, right? So we're looking at the plus or minus 2.2622 here. And if so, which it is, then we reject the null hypothesis, right? So next step, what we need to do is compute the effect size. And so our effect size is the observed deviation between the means and divided by the standard deviation of the deviations. So again, step 3b and 3c in our previous couple of slides. So after calculating this, we're looking for the absolute value of the Cohen's d, and what we find is 0.767. Which is a large effect. So it's a large effect because it is close to 0.8. And if you read in your book, a Cohen's d close to 0.8 is considered to be a large effect. And so what this is telling us is that students' GPA in Dr. Collins' stats course has changed significantly after taking his class compared to before, and it gets better after taking the class. And so when we're creating our results interpretation section, it's absolutely necessary to include this information here, the statistical information that you have created. And so this little number here is our degrees of freedom, so our n minus 1. This here is our step 3, our test statistic, or our t statistic. And this here is our Cohen's d. And so this little p-value is that alpha level, right? So if this score is beyond our critical value, we say that it's less than 0.05 because there's less than a 5% chance of this occurring, this difference occurring just sort of by chance. So effectively what we've done here is we've taken a sample of my students, we've split them into, or not split them, excuse me, have taken their scores of pre and post, right? So pre entering the class and post exiting the class, and then we compared their means. And we asked the question, are their means significantly different from one another? And so now you've gone through all of paired samples t-test. I hope this was informative. So again, just to summarize, paired samples t-test is used to compare the means either from the same sample, using usually with pre and post, or compares means of paired samples. And the calculations are identical going through both.